Good morning, good afternoon, and good evening, everyone. Welcome back to the Spring 2022 Hackathon. Hope everyone's been learning a lot. So I'm starting my morning over here. Get to start it with a really cool subject, upgradable smart contracts. This is like a super important topic if you're going to ever dive deep into the smart contract world and start developing some really interesting dApps. So get some coffee if you need it. This one's going to be really heavy on explaining the kind of how this all works. So we're going to spend a good time up front talking about that. We will dive into a demo at the end where we deploy some basic upgradable smart contracts. And this will be very EVM focused. Solana does have native features that allow upgrading smart contracts, so it's really not too bad on there. But yeah, we'll be focusing on the EVM. So if you don't already know me, my name is Zach Ayash. I'm a developer advocate at Chainlink Labs. I'm a big fan of Web3, if you didn't already guess. And yeah, I'm just excited to be here. So I want to start this off with a little story about myself. A little story about my good old Tesla. So the story of how I got it, and I'm not bragging. You'll see where this is going. I've owned old cars most of my life. The newest car I've ever owned before this Tesla Model 3 was a 2004 Mazda 6. So about a year and a half ago, I decided to treat myself to a nice futuristic car with all kinds of new features that was just constantly changing. And then this happened. So this was like a little before a year that I had the car, and unfortunately got in an accident. Wasn't my fault. No one was hurt, but my car was busted and I couldn't drive it for 6 months, and I was devastated. Luckily, I just recently got it back, actually this past week. So I've been happy about that. But you see, the thing is, Teslas are always upgrading, right? So I got it all back and it was all fixed and new and looking great, and all the physicals were nice. But I noticed that the UI had completely changed, right? And it was noticeably worse than the previous one, in my opinion. So you see, Teslas, they update all the time over air. And this puts a ton of responsibility in the hands of the software developers working on the Tesla UI. So luckily, it was just a UI inconvenience and not something worse. The Tesla engineers are pretty good about not putting anything too terrible in the code. But upgradable smart contracts are much the same as Teslas. You could only, instead of people's lives in the car, you have billions of dollars and people's livelihoods and people's future in these smart contracts. So this is a very important subject to make sure you understand what's going on and you get it right. So we're going to talk a little bit about the what and why of upgradable smart contracts today. We'll move on to the migration pattern, which is a very basic pattern of upgrading smart contracts. And we'll get into the meat of it, which is in the Proxies overview. So this is the most popular type of upgradable smart contract. And then we'll dive into the demo. I'll try to answer some questions throughout, and in sections in between these sections, and and then we'll try to also. This may go on the whole time, so we'll try to get some time for a break in between, maybe halfway. All right, let's go ahead and dive in. And yes, GM everyone, good to see everyone's having a good start or into their day, maybe middle of the day. All right, so upgradable smart contracts, isn't that an oxymoron, right? Smart contracts are supposed to be immutable. And now we're talking about upgrading and changing them. And yeah, it kind of is, right? You see, the code we deploy to a blockchain is immutable. But we can have that code encoded in it to say we can change it, which is funny, but it is possible. So like think about variables. We can deploy a smart contract with variables set to certain values, but we can change those values later on if the code allows us to. So a really basic form of upgradable smart contracts is governance, right? So governance is really a type of upgrade. DAOs often decide how and when to change parameters via governance methods such as token holder voting and using multi-sig contracts. So here's a little snapshot I took of Compound about a day or two ago. And you see they were voting on some risk parameters on the Maker and Aave token. If they were going to deploy some implementations and some partnerships, right? So why is it important that we want upgradable smart contracts? Well, while the immutability property of smart contract logic has a ton of value, and very rarely are things designed and implemented perfectly the first time. Traditional software is updated for a variety of reasons, including bug fixes, adding new features, and performance improvements. If you've ever owned any computer ever, you know what I'm talking about. And sometimes the parameters of an app have to be dynamic and change to optimize for different external conditions. If you've ever used a rideshare service like Uber or Lyft, you know that the price per ride isn't static. It depends on a lot of variables, including the length of the ride, the time of the day, what kind of traffic is going on, and how many drivers are currently active. And as always, the engineering, mantra that all of these are tools, all these techniques we're going to go over are tools, and every tool has its trade-off. It has the situations that it's useful for, right? So throughout this workshop, well, we're going to talk about a couple of different methods for upgrading smart contracts. I just want you to keep in mind as we go through these that these are tools. They do all have trade-offs, and they are all appropriate in their own ways, depending on what you want to do with your smart contracts. And we're going to discuss some of those. So this will take us to the first topic, the first kind of upgrade, which is a migration. So one of the most basic ways to upgrade a smart contract is to create a brand new version of that smart contract and just deploy that somewhere else on the blockchain to a completely new address. You then ask all your users to just start using the new one instead of the old one, just like Alice is above. You just then tell everyone, hey, move over here. You're done, new contract upgraded, but not quite. It can be really tough, of course, to reach everyone, right? And this means people can be left using the old version if you're not effective in getting out the message. Or maybe people are just stubborn and they don't want to move because that's how people can be. So if we look on the left contract here, we have contract A, has two variables and a function, do cool stuff. So then we just add in our new function, do cooler stuff, instead of do cool stuff. And we redeploy it. It has a brand new address up at the top. And that's, and then Alice is over here. Hey, everyone, move over to this contract. So this has, of course, these are the trade-offs for this method. It is very decentralized, right? People can opt in into moving into the new contract if they want. It's very similar to forking a blockchain, where users have to socially decide to move to the new chain. We have more, this keeps it very decentralized. there's no controls that can be sent off to some group that some group can kind of gather control of, like in token holding voting, for instance, token holder voting. Cons: it's impossible to ensure that every single user knows to move, and you never know that the old contract you could have upgraded because it poses some kind of security risk. So you could have a bunch of users still on an old contract that's vulnerable to something like a reentry C attack or an Oracle attack, and they could lose a lot of money by staying there. And the switch naturally imposes friction to your users. So if you're going to constantly upgrade your smart contract, you're going to have to constantly tell your users to switch to the new one, have all of the front-end applications switch to pointing to the new smart contract. And this can just pose a ton of friction to your users. And in the software world and really the design world, friction is the enemy, right? And in terms of making very usable and UX-friendly apps. So if you're iterating quickly on a smart contract often, this may not be the best pattern for you to use. So let's talk about proxies now. This is the next and the biggest kind of class of upgradable smart contracts on the EVM. Let's talk about what a proxy is in general. Proxies are generally defined as the authority to represent someone else or a figure that can be used to represent the value of something in a calculation. Essentially, proxies are a stand-in for someone else. Think about going to traffic court and getting a lawyer to represent you there. They're essentially your proxy in that court process. On the web, proxy servers sit in between you, the person surfing on your web browser, and the server that you're visiting. So if you connect to a VPN, which uses proxy servers in the middle, that VPN will sit between you and the website you want to go to. So let's say you connect to your VPN, you go to www.google.com. That request will first be sent to the VPN, who will forward it to google.com on your behalf. Google.com will see this request came from your VPN and send it back to that VPN, who sends that response back to you. So the VPN sits in between you and the web server you want to go. The VPN is essentially acting like you on the internet. And just like a proxy server sits in between a user and the server they want to communicate with, a proxy contract sits in between a user and the smart contract they want to talk to. It can forward transactions to another smart contract. So in this diagram, we have the user, they're using MetaMask to communicate with this proxy contract here. They send a transaction. It's got a message.sender, message.value. And they're calling this forward function with some data. The forward function, we don't know what the implementation is, but all we know is it forwards it to this contract, and it eventually calls do cool stuff on this contract. And we get to do some cool stuff with the smart contract. And so with a proxy contract, we can actually change the contract that it points to. And this lays the foundation for proxy style upgradable smart contracts, right? So here in this diagram, we've now changed this variable contract pointer. And instead of saying it's this address up here for contract B, we've put the address for contract C. The same function forward is still there and it's still forwarding to do cool stuff. But as you'll see, the function do cool stuff in contract C really is doing new, cooler stuff on the inside. I know these terms are very technical. So, this way the user can stay pointed to this proxy contract, but you, the developer, can change the contract that the proxy itself is pointing to. And in this way, you get an upgradable smart contract design. So you may be asking, if we do that, how do we keep the same state across smart contract upgrades? Let's look at this example. So again, we've switched our pointer from contract B to contract C down here. We're saying function forward to do cool forward to do cool stuff in contract C. But since this is a brand new contract, contract C has a new instantiation of its state, and these variables, user A tokens and user B tokens, are reset to 0. While the state was stored in contract B before, and user A had 300 and user B had 400 tokens. So that's not good. So that means every time we upgrade our smart contract, all our users are going to lose all of the information they interacted with. That kind of makes it useless, and that kind of really defeats the purpose of blockchains, right? And having this kind of global state. This is why proxy contracts themselves must store all the state. Every time we deploy a new implementation this way, we won't be resetting any state, right? So here we've moved those state variables, user A tokens and user B tokens, onto the proxy. The proxy is still pointing. We've shifted it to contract C, still forwarding, and now user A and user B retain their 300 and 400 tokens respectively. So because the proxy is storing all the state, really instead of a pure forwarding function, we need the proxy to borrow the functionality from the contract it is pointing to and run the contract on the proxy state. We'll talk about how we implement this process in a moment, but just imagine we had a function called borrow cool stuff instead of forward. And this actually took the cool stuff function, pulled it into proxy temporarily, and used it to interact on its state. And a little bit of terminology here. When we use proxy contracts to create upgradable smart contracts, we call the contract the proxy points to the implementation contract, since it contains all the functionality of the smart contract, but it really shouldn't contain any of the state of that smart contract, right? So you'll see here, the proxy again is only state and borrowing functions, right? Functions that borrow from the implementations. And the implementation simply includes all of our business logic, like do cool stuff. All right, before we dive into a little bit of the low level of how this all works, I'll go through some questions in the chat. All right, can you make a video on how to reduce the gas costs in our smart contracts? Yeah, there's actually a workshop later today that is on EVM opcodes and optimizing gas using that. So if that's what interests you, definitely try to make it out to that workshop. Yeah, opcodes is a really interesting field, interesting thing to study, in my opinion, and you can really get some cool gas optimizations with that. What if a state needs to be removed? That's an interesting observation. So, when you're updating your implementation, it would be possible to add in a function that removes some kind of state. So, like, let's say you're going, let's go back and look at our contracts examples. If you're going from contract B to contract C, the function and do new cooler stuff here, or we can create a whole new function like erase token user A tokens, right? You could do that, but as you can see, This is something that could be very dangerous, right? If done improperly. In this case, it could be erasing a whole user's tokens, which is not good. In general, this is something you wouldn't want to do, right? All your users are using your smart contract. They expect their state to stay their state, and so this might not be something you want to do. But if you do decide, hey, I'm just changing a flag or some kind of indicator in my smart contract, then just make sure you're getting your smart contracts audited and you're doing it properly. What? Oh, let me show this. What role does upgradable smart contracts play in auditing? So auditors will definitely look at your upgradable smart contract scheme and see how it works and see if there's any risks to the users. They play a very big role in the audits, and that's why all of this is so important. So when you're implementing this, you understand what kind of trade-offs you're introducing to your users with different schemes, right? They're going to look and see if you're upgrading it, what accounts have the ability to upgrade those smart contracts, and who's holding the keys, and what can you change? What kind of functionality is in the implementation? Going forward, we're going to talk a little bit about how some of the standards limit developers and how much they can do, and that's generally a good thing. How about inheritance hierarchies? That's a great question. I mean, I don't talk about it a lot in this video, but you can have inheritance hierarchies in this. Of course, that requires all of its own kind of covering, but you can do inheritance stuff. It's just gonna come with its own hassles. Is the proxy a smart contract? Is the proxy contract itself upgradable? Yes, the proxy is its own smart contract. It points to another smart contract. Again, like in this example, this proxy is a smart contract, and it's sitting in between this user and contract C. So yes, and yeah, you could actually make the proxy contract upgradable. You could feasibly imagine a third tier of contract that sits in between this user and this proxy, and then contract C. But then we're just going into like proxy inception. Generally, you don't want the proxy to be upgradable, right? Like this is kind of the whole point of proxy and implementation. Proxy stays stable. Your users just point to that. The implementation is what you change. Oh, this is a tough question. We got Melody. Where is the cat? Yeah, my cat is in my room, so he doesn't knock over any of my streaming equipment or chew on any of my cables or genuinely annoy me while I'm presenting. How easy is it to roll back changes during a failed upgrade? Not easy, right? Once you upgrade a smart contract, it goes out there, and users are going to start using it immediately because the pointer will point to that on the proxy will point to the new contract, and so we go here. The proxy is pointing to contract C now and is doing new cooler stuff. But if that new cooler stuff turns out to be not so cool and risky to the users, they'll automatically be exposed. So this is why it's really, really important to get this right up front, make sure everything is set, and every upgrade is reviewed. It's transparent. Your users can see that it's about to happen. The code is thoroughly reviewed and audited. This is all essential. What if we want to upgrade by implementing new functions? This allows that. Once you deploy a smart contract, you can't change it, right? Like once we deploy proxy, we can't add another function to proxy in general, other than forward. But we're going to talk about the specifics of how we can add functionality from contract B to contract C. Like if we want to add a new function, you can definitely do that. And one last question before we move on. That means we are not upgrading the contract, but configuring the state of proxy to route to a new different contract. Exactly. You got it. Totally. All right. So, yep, we kind of just generally talked about the proxy pattern and how we want to really borrow functionality from the implementation. We don't want to just forward, so we're acting on the proxy state. And to understand how we can do that, we're going to dive a little bit about what happens under the hood in the EVM. Specifically, we're going to talk about EVM opcodes, which, again, there'll be a more detailed talk on this subject later in the day. But when you write code in Solidity, it's being compiled by the Solidity compiler, which compiles it to what we call an intermediate language, or bytecode, right? And this bytecode is what's actually sent to the Ethereum blockchain. And this is what the Ethereum nodes run when you're calling a smart contract. And so if we want to forward a function, a transaction from a proxy contract to another contract, we really have two main opcodes that are going to be used in a smart contract in the back end, right? You have call and you have Delegatecall. And I have Delegatecall highlighted because this is the one we're going to use for upgradable proxy patterns, right? Call is totally useful and has its use cases when developing smart contracts. But for upgradable, Delegatecall is going to be the key opcode we're going to look at. And this is what we're going to focus on for this workshop. So another little background on how the EVM stores data. So we've talked, just briefly on opcodes and that there are these opcodes call and Delegatecall. But how does a smart contract store state in the background? And you'll see why this is important in a bit. So the EVM in the background doesn't know variable names. It knows what are called slot locations. And so when a smart contract is deployed, an EVM automatically creates what's called, it creates 2 to the power 256 slots. It's like an array, right? For smart contracts to store data on the blockchain. And the Solidity compiler maps variable names to specific slot locations for you, right? So you don't have to worry about the slot implementations when programming in Solidity. The compiler takes care of it. And when you initialize all these slots for your smart contract to store data, they're all initialized at the value 0 in every slot and remain that way until the value is assigned to them. And so let's kind of look at this diagram to get a good idea of what I'm talking about, right? So we have this contract A, and we have 3 variables here: user A tokens, user B tokens, and user C tokens, and this function. And so here we have each of those variable names, user A tokens, B and C. The Solidity compiles those into bytecodes and automatically replaces them with these slot locations: 0, 1, and 2, right? So 2 in the bytecode, user A tokens is this slot location 0x0. And user B tokens is actually this slot location 0x1. And this is when you deploy contract A. And they're all initialized at 0. We haven't set them to any values yet. Yes, opcodes without cats is tough. He's having a good time. He's chilling. This is his nap time. He went crazy this morning, so I think he's going to be all right. But maybe after our break later, I can bring him out for a cameo. All right, so this brings us to back to that delegate code opcode, right? Delegate call. So when delegate call is forwarding a transaction to another smart contract, it will forward that transaction in the context of the original user who sent that transaction, right? So let's look at this diagram again. This is going to be a very diagram heavy, presentation, right? And so we have this user, they're using MetaMask, right? And they send a transaction. And what I mean in this transaction is representative of their wallet, right? So it has their address as message.sender. It just says, hey, this is the address of the wallet sending this transaction. Has some may have some value of ETH attached to it. It's calling contract B. It wants to call this function, call contract B, with data, its own data. And this actually should say not call contract B, but borrow imp here, right? And so they're actually trying to call this function borrow imp, and borrow imp calls delegate call on this implementation contract variable we're pointing to right here. So this contract here. And it does delegate call, and then delegate call will keep the message.sender of the user. So this is super important. It won't replace this with the message.sender of the proxy contract. To the implementation contract, it's still this user calling, even though it's this contract actually delegate calling, right? And it keeps the message.sender, message.value, and the data. So remember what I said earlier, though. We don't want just forwarding, because the proxy contract stores all our state, and we want to have that functionality work on that state, right? That shared state among all the users. So what do you think will happen in this context if we delegate call to this implementation over here, right? So in this case, we have the user, they're sending a transaction. They're going to call this function add one to number, right? They're going to call borrow imp right here. And borrow imp is going to delegate call to the implementation. It's going to forward all those transaction values again, message.sender, message.value. And but instead of running add one to number in the implementation contract and incrementing this variable number here by one, it's going to borrow that function. It's going to run it in its own context. So it's going to run add one to number, and that's going to increment number one and the proxy. Now, remember what I said earlier, that in the back end, in these smart contracts, they really don't know variable names. They know slot numbers, and the Solidity compiler takes care of that for you, right? So when it borrows it, the function add one to num, it's not actually going to have this num plus equals one like it is here. It's going to say, hey, get that EVM storage slot 0x1 and add plus one to that, right? So turns out here that this imp variable would have the storage slot 0x0, and our number variable would have 0x1. So it's going to add one to our number. So the transaction has ended. The number in the variable, the variable in the proxy contract has been incremented by one, and the proxy no longer has that function in it, add one to num, right? It borrowed it, it's gone, it doesn't have it anymore until this function borrow imp is called again. So now you're going to see why we talked about storage slots, right? Because remember, when the proxy borrows functions and those functions change state, it doesn't know the variable names, it knows the slot numbers. And so if your proxy has state and the function is referencing a different slot number than what you want to change in the proxy, mistakes can happen, right? So let's look at this as an example. Function borrow imp is going to Delegatecall, and it's going to borrow the functionality of add one to number, right? And add one to num in the implementation contract is referencing this variable a, which is at slot 0x0 for this contract, right? And it's going to add one to that. So when the proxy borrows this function into here, it's going to say, hey, add one to the variable at slot 0x0. Well, in the case of our contract, that's the pointer to our proxy, our implementation contract, right? And so we're going to add one to this byte and all these bytes. And now you're going to break our pointer. Our contract proxy is broken. It's going to be chaos for our users. It's not a good time. And this is called storage clashing, when the wrong variable is referenced via its slot. So, we've talked about some specific opcodes, call, delegate call, and how delegate borrows. We've talked about, storage slots and how this could result in storage clashes. We're going to talk about one more low-level concept here: function selectors. So just like variables are actually identified as storage slots under the hood, functions are identified by their function selector, which is a 4-byte hash of something else called the function signature. Now that's a mouthful, I know. Let's walk through it and we'll understand, right? So again, here we got contract A, 3 variables, and 2 functions. One function, of course, our favorite, do cool stuff, because we always want to do cool stuff. And another function, add. And add just takes in 2 uints and returns the sum of those 2 uints, right? And so here we have the function name of these 2 functions. We have the function signature. Now you'll notice what all the function signature is the name of the function along with the types of any parameters for that function, right? So do cool stuff doesn't take in any arguments, doesn't have any parameters. So the function signature is simply the name. But add takes in 2 uints as its parameters, right? So its function signature is the name, but we say uint 256, comma uint 256, inside the parentheses as the function signature. And you'll notice also in the function signature, note that there is no the argument names, the parameter names aren't there. So we don't have A and B referenced here. And if you're wondering where the 256 came from, uint automatically defaults to uint 256, right? So these 2 are equivalent. And so the function signature can then be hashed. And in Ethereum world, the hashing algorithm that's used often is Ketchak 256. And after the function signature is hashed, we take the first 4 bytes out of that hash, and that gives us the function selector, right? So we literally hash the text, do cool stuff, and we get we hash it with Ketchak 256, take the first 4 bytes, and we get this function selector, right? We append 0x, and the first byte's 90, second 7b, third byte 54, and fourth byte bc, right? And if we hash the signature of add with Ketchak 256, this will be our function signature. So why am I talking about this? Well, remember, when we call smart contracts, on the back end, we think we're saying, hey, call add or do cool stuff. But really what what the EVM sees is, hey, I want to call function 0x907b54bc, right? They know the EVM knows the function selector for a specific smart contract, just like it knows slots for variables. So just like we have variable slot clashes, we can have function selector clashes. It is rare, but it can happen. And this can be very dangerous, just like the slot clashes. So let's look at two functions with the exact same selectors, right? We have the function collate propagate storage, which takes a single by 16, and the function burn, which takes a uint. And both of these functions have the same function selector, right? So when you pass in to the contract this function selector, it's just going to pick the first one that it sees. So if you say, hey, you think you're going to run burn, your smart contract might actually run collate propagate storage, and that could be doing something malicious, right? Or it could have unintended consequences to what the user wants to run. This won't occur too often, right? It has about a 1 in 4 billion chance of happening, but that's still, a chance, and it's something we don't want to risk in our smart contracts, right? If you're developing a smart contract, so let's look at contract A here. The Solidity compiler would actually catch this, right? It would prevent this from happening within the same contract. So the Solidity compiler will say, hey, collate, propagate, storage, and burn, they have the same function selector. You can't compile this. Don't deploy it. This is not good. And so we don't really have to worry about it so much within the same contract. But remember, we're talking about proxy implementation patterns here. We're forwarding or borrowing from one contract to another. And so between two different smart contracts, they may very well have function selector clashes, right? So let's see. So let's look at this example where this could happen, right? Let's just kind of get an idea. The user sends their transaction, and they're calling function 42966C68, right? Which is this collate propagate storage on the proxy, right? But it also matches with the function burn, right? So saying, okay, burn isn't actually on our proxy contract, so there shouldn't be a clash, right? Or normally, when we're using Delegatecall within our smart contracts, it's actually going to put Delegatecall within something called a fallback function, right? The fallback function is a function without a name, and it's what the contract falls back to if it doesn't know any other function to run, right? And in this case, the user thinks, hey, I'm going to pass in this this function selector, and I'm hoping that the fallback's going to run, and it's going to borrow burn because it's going to forward this function selector, and I'm going to call burn, and it's going to do some action on my smart contract. But instead, it runs collate propagate storage, and unfortunately, this this function sends the user's tokens to another address. So now when they thought they were running some function on the implementation, they accidentally called collate propagate storage, and they lost all of their tokens, right? So this obviously caused not good things to happen to our user, unexpected behavior. And this is where proxy standards come in to help solve these problems like variable slot clashes and function selector clashes, right? Let's not reinvent the wheel. Let's take advantage of people who've already solved these problems, right? And a great place to find pre-solved problems and libraries in Web3 is OpenZeppelin. They really do have great library of these standards. their code and documentation with how it all works. We're going to talk about these standards in a bit. And I'll just forward this link in the chat. These couple of links here on OpenZeppelin. OpenZeppelin. We have a GitHub repo and some docs there for OpenZeppelin if you decide you want to check that out. So let's talk about proxies versus migrations in general and like their kind of trade-offs in these design patterns. And then we're going to dive into some specific proxies later and talk about those trade-offs, right? Page not found. Go ahead and I didn't mean to think that the chat client was going to kind of compress them. Those are actually two different links, right? So we have the first GitHub link and then the OpenZeppelin link below it. So just make sure you're splitting those up. So in general, the trade-offs between proxy migrations, what are the pros of proxies versus migrations, right? In general, we can quickly switch all users to a new implementation. We can upgrade a smart contract and everyone is automatically quickly upgraded to the new contract. And this allows the developer to iterate smart contracts quickly without frustrating their users, giving them all kinds of ability to rapidly deploy and really improve their functionality. Cons. I should say I have written there lots of power in the hands of developers. It's more centralized. It can lead to that, is what I mean. It can lead, if implemented improperly, to lots more power in the hands of developers and more centralized. And it all depends on how we implement the proxy again, right? We're going to talk about some patterns here in a bit. But for instance, we can have the ability to switch our implementation and change that pointer in the proxy to a multisig, right? And that multisig could be 10 developers, or that multisig could be controlled by a governance mechanism in another smart contract and controlled by the users, right? So this can be a con if implemented improperly. Proxies add gas to every contract call compared to a migration, right? With a migration, we're just deploying a new contract, ask everyone to point to that. They still call the same functions. But with a proxy, we have this middleman, right? We have this proxy contract sitting in between us and the contract we actually want to talk to for implementation. And it has to do Delegatecall and borrow, and all of that has gas overhead. And so if you're really trying to optimize gas, that can be a con. And of course, proxies have a good bit of extra complexity that's added on top. As we've seen with these clashes, a lot of care has to be taken when you're implementing these kind of patterns. So as a general rule of thumb, if your contract is simple, it's well audited, and hasn't needed change for a while, this may not be the best pattern for you, right? You may want to just do migrations. That might be solid. An example of this is Uniswap, right? They release a version like every year and a half so far, and they're not fixing any security critical bugs, and they have a governance module to kind of oversee those upgrades, right? And so they've chosen the migration pattern, which is perfectly fine for what they need. Okay, let's see if there's any questions before we move on to talking about specific proxy patterns. So Kunal asks, will the old contract still run on the blockchain? I like to pull up these diagrams while we're talking about proxies, so we kind of have the mental model there. All right, so yeah, if we're upgrading from contract B to contract C, contract B does remain on the smart contract. It's still there. It's just simply our proxy isn't pointing to it. Once something's on the blockchain, it's on the blockchain. It's there. So yes. I wonder if layer 1 and layer 2 run on the EVM. Yeah, so everything that runs on Ethereum runs on the EVM. So even layer 2 is run on the EVM. And what is the difference between the beacon chain and the EVM? So the EVM is the Ethereum virtual machine. I should clarify this a little earlier, right? So the Ethereum virtual machine is what runs all of the smart contract logic. It manages smart contract state. It is like kind of the smart contract magic on all like Ethereum type chains, right? The beacon chain is this concept in ETH2 of this kind of like this like lighthouse, this beacon chain, right? That kind of coordinates all these other chains attached to Ethereum. I won't go into the detail of ETH 2.0, but the beacon chain isn't really a thing for smart contract developers at the moment because the merge hasn't happened yet where the beacon chain is like merged in and all this stuff. So really, you just got to be concerned for now about the EVM and how that runs smart contracts. How does the program know to assign a slot to the variable number? So let's bring up the slide there with the slots. Yeah, so again, when we went through this delegate call function right here, we were borrowing add 1 to num, and originally this function had num plus equals 1 in it. It was referencing num, the variable in this implementation. And we borrowed it, and it automatically switched num to storage slot 0x1. And how did it know to do that? Well, remember, we're looking at this as Solidity code, right? But this is really all bytecode on the blockchain, right? So in the background, there is no num plus equals 1 on the blockchain. There's only, this actually says in the bytecode storage slot 0x1, right? So we're just borrowing storage slot 0x1 plus equals 1, and that's coming into the proxy. So the Solidity compiler handles all of those kind of conversions for you, and then you deploy the contract, and it's referencing all the proper slots for you. So essentially, the Solidity compiler takes care of it for you. Great question. Are there best practices on code governance to allow, disallow upgrades? Only owner or other approaches? Yes. We'll talk about some of those coming up here in a bit to patterns that you can implement. But yes, there are some best practices. Security, again, it all depends on the nature of your smart contract and what you need out of it. Perhaps you have not a very security critical smart contract that you're iterating a ton on, like some kind of game. And, you don't need like a whole governance module and a multi-sig and all these different approaches at first. It really all depends, but we'll go over some of that in a bit. Are we going to see in the hackathon how to do a proxy? Yep, I'm actually going to go over a demo at the end. And awesome. Thanks, Alex, for posting that link. Yes, that is the GitHub link for the proxy contracts. A great place to check out and see these implementations. Are all proxies moved at once in implementation, or can select few be moved to an updated contract? For example, for access to premium functionality for a protocol. So in general, if I'm understanding this question correctly, when we're upgrading, it's all at once, right? So we write our contract C that has the new functionality added in. In this case, we just edited, let me get that off the screen. In this case, we just edited do cool stuff and added newer functionality to this function, but we could have added another function as well, a function do awesome stuff here, right? And then when we upgrade contract B to contract C, when we upgrade those contracts, it'll upgrade it all at once, right? We're changing the pointer, we're pointing to contract C, everything changes all at the same time. Now there's different patterns. There's patterns where you split up the functionality. So this is possible, but in general, for what we're talking about today, it happens all at once. So hopefully that answered your question. Let's go ahead and move on. All right. So, we kind of covered all of this. We started talking about how we want to implement these specific proxies. There are some questions about that. So now that you understand how proxy contracts work in general, how the delegate opcode works, and why we need to be very careful with these patterns because of things like function selector clashes and slot clashes, I think we're ready to start talking about specific implementations of proxy standards, right? And their trade-offs. So a really prominent one, and one we're going to talk about today, we're going to go over this one in the demo, is the transparent proxy pattern. So I'm going to go over a very simplified view of this pattern here. So essentially in the transparent proxy pattern, we make sure, as always, to have all of our state and all of our functionality, or all of our state in the proxy and all of our functionality that does anything important in implementation, right? We have some functionality here in the proxy, but the only functionality we have in the proxy is borrowing functions from the implementation. And in transparent proxy, we also include any of our update functionality, right? So in this case, we have this function. Let's update our implementation address, right? It's going to be a function. So in the transparent proxy pattern, we include this functionality in the proxy itself. And what we do is we restrict access to any update functionality to some kind of admin, right? And the admin, again, it could be a single developer. It could be a multi-sig of developers. It could be a multi-sig controlled by governance, all kinds of things. But the function for our delegate call, this fallback function here, it has this restriction of no admin. So it won't allow the admin contract to run the fallback. It's going to check for that. And this helps us prevent function selector clashes. Remember earlier when we didn't have these kind of protections on, and let's say update imp ended up having the same function selector as burn, well, that could cause all kinds of chaos for our users, for our devs that want to just simply update the implementation pointer. And so now when our dev calls a smart contract, the admin can only call this. It will never delegate call and bring in burn in from there. And this really helps with function selector clashes, right? And our users, they can update our smart contract, which may be what we want, right? We don't want anyone being able to come in and just point our proxy to any other contract. That could be extremely risky, right? And so this is the transparent proxy pattern simplified. I'll add a link here in the chat to the EIP, right? So this is an official EIP. It's been passed. This is a well-known pattern. And of course, you can always read up more on this in the Open Zeppelin docs. They have a lot of good stuff talking about transparent proxy patterns. And we'll be walking through this later so you can kind of see it in action. The other big one is universal upgradable proxy standard. So in our UPS, right, UUPS, right, in this standard, all of our upgrade functionality, so basically all of our functionality is in the implementation contract. And so because all of our functionalities in the implementation contract, other than our delegate call, of course, the Solidity compiler will again help make sure that there's no function selector clashes here, right? It'll catch it before we put in a new implementation contract. So there's no admin rights here. We just have an implementation contract with all the functionality. Solidity compiler makes sure, hey, there's no function selector clashes, and we're good to go. Now, of course, there's trade-offs here, right? And when you're using transparent or UPS, right? What are those trade-offs, right? In general, transparent proxy pattern, of course, like both of these, it solves function selector clashes. So both of them are good for that. And when designing transparent proxy using the transparent proxy pattern, it's very explicit on who can run what function. So if you're reading that code, you know just from reading it, oh, this function is run by the admin, or this function isn't run by the admin, right? This is run by the users. So that this explicitness can be a pro, right? Cons, because we're adding all these extra checks in between our functions in the transparent proxy trade-off, it adds extra gas. So again, if you're gas constrained, that might not be the route for you. UPS, again, solves function selector clashes. So they both have that. And it saves gas per call versus transparent proxies because we're not checking. We just have everything in the implementation contract. And there's also kind of a cleanliness here, right? Where our implementation is literally all of our business logic, including the upgrade logic, right? So it's very just cleanly separated. Proxy, state, and borrow. That's it. Implementation, all of our functionality, including upgrade functionality. Clean, love it, chef's kiss. But cons, if all upgrade logic isn't included in the next implementation upgrade, if you leave off some kind of upgrade logic, like of the function change the pointer in the proxy, your users can be frozen onto that proxy, and you can be frozen from upgrading it further. Now you're back to the migration method, and you're like, I can't upgrade the proxy anymore. We have to migrate to a new contract. So it's really important up front to make sure when you're upgrading using the UPS pattern that you have everything you need in the implementation. All right. And there's more than this, right? So we have diamond pattern, which actually splits the implementation contract even more into all these different implementation contracts, where each implementation contract is a specific function all on its own. So there was a question earlier about, if you just want to upgrade specific functions, this can kind of give you that power. So you may want to look into the diamond pattern more. I'm not going to go into detail in it for time in this demo. You have the metamorphic pattern, which is like a factory pattern, which allows smart contracts to completely write over themselves, right? Like just completely change the bytecode of a smart contract and how you think a traditional upgrade would work in a traditional system. Of course, that has all of its complications and trade-offs. And there's probably going to be more to come, right? The landscape is changing fast. Who knows what patterns people will discover and what new technologies will be used to create new upgradable patterns. So we're about to dive into the interesting part. We're going to go into the demo. So now you kind of have a good understanding of how this works. So when we're actually writing the code, I'll try to reference some of these topics again. I see we have a question. So I'll answer this question And then I'll give everyone, let's see, a 5-minute break. I'll come back, go use the bathroom, drink some coffee, maybe put some questions in the chat. I'll try to answer a couple when we come back, and then we'll go through the coding demo. So Gabrielle asks, which is message.cinder for a contract behind a proxy? The real message.cinder are the proxy address, right? So let's go back. When we're using Delegatecall, the message.cinder is of the original person who sent the transaction. So this user sends a transaction to Proxy. The proxy is running Delegatecall, and Delegatecall keeps the context of the original user. So it's the message.cinder of the user, right? Not the proxy. Get the cat, please. All right, yeah, I'll go get him. I'll come back from the break a little early, so if you have some time, I'll show my cat, and then we'll move on to the demo. All right, everyone. I'll be back. See you in 5 minutes. Get ready for some coding. All right. So I'm back here a little early. For those of you, we had a couple of requests in the chat to see my cat. Here he is. He's a cute little dude. His name is Coda. Love him. He can get a little rambunctious and get into trouble when I'm in class and giving talks, though. So I try to keep him in my room a bit. I'll give another minute, and then we'll dive into the code. If you have any questions, feel free to drop them in now. I see we do have some. Where can I see all the available public contracts? I'll be posting those in a bit. Yeah, there's a GitHub repo. Let's see, I can pull it up right now. Currently, it's under my GitHub username, but we're going to be moving this to the Chainlink general repo. So when we don't use Delegatecall, then it's the proxy address. Correct. Yeah. If you're using call, it's just going to forward the proxy address instead of keeping the context of the original user. Yep. Correct. That's one of the main reasons we're using Delegatecall, other than the borrowing functionality. I'm glad y'all are a fan of Coda. Yes, he is a very big cat. I got him when he was a kitten, so I had no idea he'd get this big. But he is a big, of course, scaredy cat, like a lot of cats are. Big softy. Love that cat. Okay, let's go ahead and get on going with the cool code. And so, why did I say that Tesla example, right? Well, again, Tesla's upgrade a lot. So we're going to try to do this coding context, make it a little fun, built in the context of an upgradable Tesla power module for the car, right? So oftentimes what they'll do is they'll find some kind of improvement in how they're like doing the thermals of the car or whatever, and it adds a couple of points of extra horsepower that the car can then access and keep the same efficiency, right? So that's what we're going to be doing. We're going to be changing and adding implementations to this like power module on our car and upgrading it. This is going to be using the transparent proxy pattern, right? So that's the one we're going to use for this demo. We're going to use what's called the Open Zeppelin Hard Hat Upgrades plugin, right? So it's going to be in Hard Hat. And we're going to upgrade our smart contract, right? That's what we're all here for. So let's go ahead and dive in. Pull up VS Code here. Second. And so let's share that. Now let's share to do. All right. Okay, so I'm in VS Code, and actually where I've gone and started is cloning the Hard Hat starter kit, right? So I like to start a lot of my work from cloning the Hard Hat starter kit, the Chainlink Hard Hat starter kit, even if we aren't going to be using a lot of the Chainlink functionality in this demo. It's just convenient because it already has a lot of the pre-config stuff in our Hard Hat config. All this is kind of already set up, every library that we may need. You get a lot of already built-in tests and tasks. So I actually like to start a lot of my projects just straight up from the Hard Hat Chainlink starter kit, right? And if you want to know where to find that, let me go ahead and get that link for y'all. So you can clone it from this link here on GitHub, right? So this is a fresh clone of that starter kit. All right. So we've got that. The first thing we're going to do here is we're going to add the Open Zeppelin library that we're going to use for this, right? So we'll open a terminal in VS Code. Wait for it to load. We'll say yarn add at Nomic Labs / hard hat ethers. This will add that package in. And while that's being added in, we're going to want to add a require statement to our hard hat config, so hard hat knows that this is a package we're going to be using throughout our programming experience today, right? So we're going to make a require statement here. We're going to say require, and again, we're in hardhat.config. And we're going to say at open Zeppelin / hardhat upgrades. So save that. And yarn is still adding there. So while that's being added on, let's go ahead and start creating our smart contract that we're going to be using today, right? So we're going to go into contracts. I'm going to create a new file. You see, since this is a hard hat starter kit, we already have all these awesome Chainlink examples. If we want to use those in our smart contract, or not, but they're there, so that's nice. We're going to create Tesla power.sol. All right. So again, what we want to do is we want to create just a basic smart contract for updating our Tesla's horsepower, right? This like power module. As always, we'll start with our pragma solidity statement, telling the compiler what version of solidity we're going to use. We're going to go with 3.7. And we're going to call this contract Tesla power. All right. So we're going to need a variable that we're going to change. We're going to make it a uint256. It's going to be a private variable. So we're only going to change it via methods internally. And we're going to call it horsepower. So this is going to represent the horsepower of the Tesla, right? We're going to create an event. And we're going to call it horsepower changed. We're going to call that, we're going to put that in here as uint. It's going to emit a uint256, and it's going to emit the new value when we change that horsepower, right? That's going to be the purpose of this event. And we're going to make a function. This is going to be our setter function, set horsepower. And this is going to take a uint256. New horsepower, public, not public. And we're going to do horsepower equals new horsepower. Okay. So this function is going to take in a value of uint256, and it's just going to replace our variable horsepower with whatever we pass in, right? So we can pass in whatever we want. It's going to set our horsepower to that. Of course, we have that event, so we're going to emit the event horsepower changed to new horsepower. Lastly, let's just put in some getter functionality here. So a function whose only purpose is to read that variable. So we're going to call it retrieve horsepower. It's going to be a public, and since this is just reading state, not doing anything else, we'll make it view. It's going to return a uint256. And we need returns up there. Do that mistake all the time. And we're going to return horsepower state variable. And that's going to be our Tesla power smart contract, right? So let's go ahead and save this. Yarn is still doing its thing. This is because it's the first time I've run Yarn on this repo. So it's actually not just adding in that one package that we asked for, but it's installing all of the node modules we're going to be using. So that's why it's taking some time down here. All right, so we have our smart contract here. Now, of course, something that I always try to get in the habit of, I think any good developer should get in the habit of, is writing tests as we're developing our smart contract, right? A little test-driven development. So let's make a basic unit test for this smart contract. We're going to put it in this test directory here under unit. We'll call it, let's see. That's not what we'll do. Go here. We're going to call it Tesla Power. So the name of our contract. Unit test following the conventions down there. .js. It's going to be a hard hat test here. Oh, did I not? Looks like my VS Code is running a little slow right now, probably because of all the stuff going on with Yarn. Let's give it a second here to catch up with everything. If it freezes, we can switch to a different VS Code. There we go. Perfect. All right. So, yep, we created that. Yarn finished too. It was doing a bunch all at once. And yeah, let's go ahead and write this unit test. I'm going to put a lot of the boilerplate to save time here as a copy and paste, and I'll just kind of walk through it. Let's see here. So we'll put in all of the imports. I'll just copy and paste those in. And then I'll put in the describe statement, and I'll actually type through the tests with y'all live. Okay, so here we're saying, all right, we're going to put a describe statement in our test, and we're going to say, hey, this group of tests in this file is going to be for our Tesla, and eventually it's going to be for our proxy contract. And all we want in this test is it is going to retrieve value previously initialized, right? And so this is going to be an async function. Retrieve that. For this test, our test is going to be async function. Then we'll describe the test in here. Okay, so what are we going to do? Well, first we're going to need to grab our smart contract that we wrote. So we're going to create two variables. We're just going to call one uppercase Tesla and lowercase Tesla up here and state there. And we're going to say uppercase Tesla in this test is await ethers.get contract factory Tesla power, right? So what this is going to do is going to grab our contract from up here that we wrote in our contracts folder. It's called Tesla power, and it's going to bring that in, and it's going to assign it to this variable Tesla. And then we're going to have Take a little Tesla, say await, and this is where we're going to call in that upgrades open Zeppelin that we added in throughout our hard hat folder. So we're going to say upgrades dot deploy proxy. Right, so this will take care. This function will take care of deploying all the contracts we need for the transparent proxy pattern, right? So this is going to take our Tesla power. It's going to take all that functionality and deploy it as an implementation contract, have a proxy contract that points to that implementation, and also have a third contract called the admin contract, which will handle all those admin privileges we were talking about earlier, right? So we're going to want it to deploy the Tesla contract. And we're going to set the horsepower to 600. And I'm going to talk about why we're doing this in a second. And let's see. We will set it, the initializer here. 600. Oh, I'm typing what we had up there again. Look at me. Sorry about that. But you got an explanation of what's going on up there a little earlier. That's what's going on up there. We're going to expect. Now we're going to make our expect statements, right? So that's what we're doing. We're deploying our proxy contracts. We're going to take the Tesla. We're going to initialize it with 600. And our initializer is going to be this function. Now, implementation contracts can't actually have constructors like you would in a normal smart contract, right? So because if we had a constructor, right, it would have that would be a function that would initialize state in our implementation, which is what we don't want. And with this horsepower, the upgrade function will take care of separating out that state into the proxy. So Open Zeppelin has got us on that. So that's why we're saying, hey, since we don't have a constructor, we're going to have this set horsepower function as an initializer, right? This is going to be the function it runs immediately after deploying, right? So it's going to deploy it, and then this library will take care of calling that function for us and passing in the value 600 and setting our horsepower to that, right? So let's go ahead and write our first expect statement, right? So we'll say await Tesla. So we'll call our deployed contracts, and we'll say retrieve horsepower. There. Then we'll put to string. So we're going to convert what we get. So we're going to call that retrieve horsepower function on our deployed contract, the implementation. We're going to retrieve the horsepower, and since we set it to 600, it should be equal to 600. Right? And have one more expect statement. We'll save this one. We'll save this one for later. Now we're just going to figure out why is it giving me this error here. So good. Got that. Let me just look through. There's probably a parentheses I forgot to close here. For each. It's good. Oh, that was right. It after our it statement. fun with coding is that you always get these little things. I see what it is. Function here. No, async function. That's right. So horsepower. All right. So I don't know, to save some time here, I'll just copy and paste the code. There's probably some parentheses in here that I am missing. So I'll throw in the same code, just properly. Okay, and we don't need this expected. Okay, so it's still giving me that, so that means it's something, because I didn't close the describe. That's it. Cool. All right, there we go. All right, so always with programming, the parentheses and the curly braces. That kills me. But all right, we got that going. We got our first test on there as we're developing it. And we can just run yarn hard hat test. And it's going to run that. Okay, and of course we're going to get that. Oh, it didn't actually add in our hard hat upgrades. All right, let's go ahead and go back, create a new terminal. I don't know why it didn't. I guess it was focusing on doing the yarn install for everything and didn't actually add in. So we're going to make sure yarn add Nomic Labs / and make sure I get this name right. We'll go back to our hard hat config. We're going to add in that opens up. Oh, this is probably what I did wrong. I'll probably add in at Nomic Labs. So we're going to add in at OpenZeppelin / hard hat upgrades to the end here. Slide that package so you can actually see that. So while that is adding, yeah, thanks for pointing that out, Shaman, missing the end of the describe. Thanks for that. Did I misspelling horsepower? Where do I got it misspelled in the test script? Let me know where I'm misspelling it, if I'm misspelling it somewhere, and I'll change it. But we'll see real quick if there's a compile error, right? So yeah, again, what this deploy proxy is going to do is going to deploy all 3 of our contracts for us again. So if we run this test, it should do that. So now we're going to run yarn hard hat test. It's going to do its thing. All right. It's running through everything. It's compiling everything. And so since we're using the hard hat starter kit, it's going to run through all other tests real quick. So only take some time the very first time we run it. But while that's going, all right, of course, more errors. Perfect. Live coding. Let's do it. Ethers isn't added in as a context in this. All right. Yes, we didn't add ethers into our require, of course. That's a very important package we want to add in there, right? So let's go in and we'll just get the require statement for ethers. Oh, save this here. There we go. SBS, SPDX. See what this comes up with this time. Still not finding that ethers. Okay. One second here. Let's see what could be going on. Ethers do our hardhat.config here. Looks like I've got everything added in there. Let's just do one more thing, and if this doesn't work, I'll just switch to the working code, right? But we'll try to add in, we'll do yarn add, and we'll add in the at Nomic Lab / hardhat ethers. Again, I think I did it at the beginning, and I think because it went through that whole yarn install, it didn't add it in. So we'll see, hopefully this works. But it's gonna take some time, of course. So while that's going, and we'll run our test when that's done. Let's go ahead and move on, and we're gonna make a contract, an upgraded version of our Tesla Power contract. So when we deploy it, we'll see what we're going to upgrade to, right? So we're going to call this one Tesla Power v2.sol. Right. And what we're going to do is we're just going to copy all of our Tesla Power contract. And we're going to add in a single extra function. So instead of setting the horsepower, we're going to make a function that increments it. Usually you don't get giant gains in horsepower, even if you're improving efficiency. So maybe you just get 1 horsepower extra at a time as they improve the technology of the car, right? So UN 256. Return. So what this is going to do, return anything. What am I doing here? We're going to all we're going to do is we're going to take our horsepower. We're going to add 1 to it. So we're going to increment our horsepower. And that's it. Plus plus just means take horsepower, add 1. Make sure that's saved. And it looks like our yarn add has gone through. So let's fingers crossed. Do yarn hardhat test one more time. We're going to go back and hopefully our tests run. And let's go. So we have our 2 contracts, and after we deploy this Tesla, the original Tesla Power contract, we're going to upgrade it to the Tesla Power V2, right? So we're getting one more error. Still not finding it. Okay, so to save time, let me switch to a different VS Code, and I'll go from there. So 1 second here. Sorry about that, y'all. Yeah, our test is passing. The others are throwing the error. Yeah. I probably forgot to add a yarn somewhere in the steps here to make sure that the ethers was added to those tests. Yeah, probably something in the setup, right? So let's go ahead and I'll share. Share this screen, right? And so here we back are, right? We got our Tesla Power V2. We got our increment horsepower on there. And we'll go back to our test here. And you're going to see a little bit of extra stuff on the test. We'll go to the other tests in a bit, right? But we still have the same logic here. You know, we're using the deploy proxy. We're deploying it set to 600. And we're retrieving it, and it should equal to 600, right? So let's go ahead and yarn test. All right. So I definitely tested this one out, so this should work out. I see. This one's pointed to Rinkby. We don't want Rinkby right now. Test network. One second. What's going on here? Default. Default network is hard hat. Why is it trying to go to Rinkby? One second, I'm trying to troubleshoot here. Notice that there's no, yep. So let's see. Yeah, that should have worked. Network. What could it be? Let's see. We've got our deploy scripts, test. Test is going through. It's calling out the hard hat config. I'm not sure why it's defaulting. I mean, we're going to want it to default to Rinkby in a bit anyway. I mean, I can go back to this shell. The shell should work because it has, even if it's deploying to Rinkby, it has everything set up in it. Yes, there we go. Perfect. I'm glad y'all could join me on this journey of troubleshooting hard hat. All right, so it's going through all our tests. Everything's running, and it's going to get to our random number consumer test. Everything is passing. Of course, it's running these other tests. I'll explain what they do in a bit. But yeah, so everything passes. at least at the beginning for what we wrote earlier, again, it right here, this all the way down to this expect statement, it's checking to make sure that we deployed a proxy contract, an implementation contract, and the state in the proxy was set to 600. So that is fantastic. All right. So we got that running. And now let's create, if you want to deploy these separately, there is a deploy script in here, right? That was created separately, right? So let's walk through this script, right? This will take this is just if you want to do this separate from the test, right? You just want to deploy upgradable smart contracts in general. In this case, we created a script called deploy Tesla power, right? And it's going to, again, get our contract from our contracts folder. It's going to actually deploy it, and it's going to use that deploy proxy upgrades library from OpenZeppelin. Right? And it's going to set it. Again, we're setting it to 600. You can change it to whatever you want. And we have our initializer, which is the function it'll run after it is deployed. And so we have, and then some console.logs. And it's that simple, right? So this is a separate script that deploys it, right? So if we want to run this, we can say yarn hard hat run scripts / deploy Tesla power. And I'll run the deploy script as a separate thing. Now, I probably scripts deploy Tesla. Forgot to add the JS at the end. So what this, so you're saying, okay, we got everything deployed. We ran the test, everything's working. Where are the proxy contracts? How is it separating out? How can I see that? Which is a good question. So to do that, we're going to go look at the transactions this wallet has been doing on Rinkeby and see where that's going. So now I'm going to share a quick ether scan. So I'll go to the ether scan of this demo wallet here. And these were, because these are actually going, I think, to hard hat now. But these are some deploys I've done earlier for the proxy contracts, right? So if we go here, we'll see it created this contract. This is the first contract it deployed. This is the actual proxy contract, right? And if we go to this one here, and we see the other contract I created, and this one actually, because this pattern has been done, this code is already verified on Etherscan. This is that admin contract I was discussing earlier. So this is the contract in the transparent proxy pattern that makes sure that only admins run the admin functions and non-admins run the non-admins functions, right? The users. And finally, let's take a look here. This is the transaction that created the implementation, right? So this is the implementation contract. Or sorry, this is the proxy. The first one was the implementation. Yeah, this is the proxy. Since this is a standard, they all look the same, right? And it's already verified. All right, so let's go back to VS Code. Okay, so we're back here, VS Code. We've gone through, we've deployed our proxy pattern contract. We have an initial implementation. We haven't upgraded it yet, right? So for the upgrade, we're going to want an upgrade.js script, right? And we're going to take our original proxy and we're going to point it to Tesla Power V2 instead of Tesla Power V1 now, right? So again, we're going to go through here. We're going to say, hey, get contract factory, pull in that contract from our contracts folder, Tesla V2. We're going to call upgrades library from OpenZeppelin. And this is where you would put in the address of your original Tesla power contract. So this right here. Right. And this will take care of doing the upgrade. It's that simple, right? We have another script here, prepare upgrade. So you may be wondering what that does. And this will just run some logic that checks. It'll run the prepare upgrade on this upgrades library here. And this just checks to make sure that like everything is good with the upgrade. And of course, you need to point to the proxy address right there, right? So now if we want to run the upgrade script, we'll run yarn hard hat run scripts / upgrade.js. Because it hasn't actually compiled our Tesla Power V2 .sol contract here, right? So there's no artifact there. Let's see, Tesla factory, Tesla V2, because we called it Tesla V2. Let's change it to Tesla Power V2. That's it. Let's run it one more time. Man, just the theme of this demo, right? Let's see. What's going on here? Saying that this isn't the right address. Okay. Let's run our we'll run our deploy script one more time. Say network rank B. Set to rank B. Oops. Deploy power. JS. So it's going to deploy this to rank B this time. We got it. Let's put this address in. So now we'll say yarn hard hat run scripts, and we'll do upgrade. Right. Make sure I got that script name right this time. Yep. All right, and so this should take our Tesla Power V2 again, and take that pointer. Of course, is it proxy with a logic contract? But take our proxy contract and point it to the V2 contract instead of the V1. Let's see what error we're getting though. Doesn't look like any are the logic contract. 67. at Rinkby. All right, yep. So we'll point to Rinkby. Hopefully this will work. If not, I'll have to unfortunately move on due to time. But I can kind of talk through the rest. That really hits all of the functionality. So hopefully this will run. Take some time to run the upgrade. So it looks like it's doing it. It's just taking some time now, right? See, it's doing this thing, communicating with Rinkby. Appreciate it. Join the debugging process. Yeah, just one of those days. I'm glad you could see it in action, right? This is what happens when you code. So hope it helped you learn, at least that we think. Yep, it seems to kind of be stuck on running here, right? So I'm not sure why it's stuck running here, but yeah, that's essentially what I would have done. I'm sorry that we won't go to see this unless this completes relatively soon. But with the last couple of minutes here, if y'all have any questions about the process, I can answer any questions. If not, we'll just kind of go over what we talked about today. So feel free to throw any questions in the chat. So I can try getting out of it and running it again. All right, well, oh, there we go. All right, so now it's on my environment variables. We can set those real quick. That's an easy fix. Now, this is a demo wallet, and I always change my RPC URLs after every demo. So I'm not worried about showing this on the screen. But again, always be careful with your environment variables. Don't ever show these to people, right? But this is, again, just a burner wallet with no real value in it, right? So yeah, we'll let that run and hopefully it comes back. But let's go ahead and quickly review what we've been over today. So we're running short on time. Yeah, so we talked about what and why on upgradable smart contracts. We talked about the migration patterns. We talked about what proxies are, the Delegatecall and EVM basics, how Delegatecall borrows, function selector clashes, slot clashes. Talked about two prominent patterns and the trade-offs in the proxy pattern space, transparent proxies and universal upgradable smart contracts. And we went through a demo with a lot of troubleshooting. But I think I'll walk through the code. You can understand what was going on. I hope that was a little bit helpful there. Unfortunately, at the last step there, we're getting some errors. I'll have to walk through and see what's going on with that. It looks like I'm getting some fee errors now. So something's going on with Rinkby. It's not setting the fee high enough. So yeah, I hope this kind of gives you an idea of how to structure proxy contract upgrades. And going forward, you can be a little bit more conscious if in the hackathon you're trying to implement a proxy contract upgrade. Really make sure you understand why you're using the specific pattern you want to use and what trade-offs are incurred from that. But yeah, thanks for following along. Please leave any feedback that you may have on the this workshop. I'll post this link in the chat for those of you. This is the actual demo here. So this will take you to this screen here. And here is the link for those of you who don't have a camera to take a picture of it, right? All right. Well, thanks for joining, everyone. Hope you learned something useful from this. Love to hear some feedback on how we could do this better. And I'll see you in the next one. Good luck in the hackathon.